Yeah. We know the critical step for the quicksort is partitioning step. Partition. Yeah. To get a partition, yeah, if we only want to get the result without considering other factors, that's not very hard. So our first try, we use two auxiliary subarrays. Arrays, let's say arrays. All right, two auxiliary arrays. And then when we do comparisons, we place the original elements to one of the two arrays based on the values comparing with P, the pivot element. Okay, if the values are smaller or equal to P, we place them in the left array. Otherwise, if the value of an element is greater than P, we place it in the right array. All right. The problem of this way is we use too much extra space. So we double the space than the original data size. We double it. All right. That is not very good because when the data size is big, then you double it. Then you use too much extra space. Although we are allowed to use a little more extra space, but we should not use too much. All right. So our next task is we want to reduce the amount of extra space. How to reduce? What is our goal? Eliminate the auxiliary arrays. So that's the main task we need to work out next. All right. Now let me describe the idea to work it out. Yeah. The idea actually pretty simple. We just use the space in the original given array in an efficient way. That's all we need to do. We do not need to copy data from the original array to auxiliary arrays. So that's the main point. But for the detail, let us fix the detail part. Okay. All right. Yeah, my remote control. All right. Control extra space used. Here, let me use the diagram to explain how do we control using extra space in some efficient way. All right. This is the this diagram gives us the, all the locations from the given array. All right. We know all these locations are occupied by the given elements in the array. Yeah. In order to move elements around, we need to use extra space, but we like to use the minimum amount of extra space. That's the main point. All right, so let's see. Yeah. When we move, we want to, conceptually split the regions in the positions of the original array. Yeah. The first region we call the S region. S means smaller or equal. Okay, smaller or equal to P. All the elements in S region should be smaller or equal to P. Next, L region. All the elements in L region are larger than P. Okay, yeah, so we know the meaning. Yeah. And when we work during the working process, there are some locations we call the U region unprocessed. U means unprocessed, yeah? Because we need to process element one by one. So we need to consider those elements that have not been processed. So we use U region to represent those elements. All right, yeah. The reason we use these different regions when we do manipulation, it's very clear in our mind what we are doing. Okay, eventually we want to move all the elements from the U region to S region or L region. That's our goal. All right. Now let's look at the states during the process. Yeah. In A array, A subarray here, that it corresponds to S region. Yeah. B subarray, it corresponds to L region. All right. Initially, they are empty. Yeah. When we start, these two subarrays or these two regions are empty. Yeah. And U region is full. Yeah. U region, all the elements except the pivot element, all in the U region. Okay. Then we grow S region or L region by comparisons. Every time when we compare one element from the U region with P value, we know where it should go. S region or L region. All right, yeah. So the unprocessed initially, that's the whole elements whole, but except P. Yeah, we know the whole here, it means because P has its special role, so we put it aside. Other than that, the whole. All right. Then at the end, it becomes empty. When all the elements are processed, then this U region is empty. Then we reach the end of the partition. All right. So look at this idea. Yeah. Here I use this diagram to describe the whole process. Right. But how to see that whole process clearly? I like to use a concrete example to show you, step by step, all the details to do the partitioning. All right. And after this example, if you follow the example closely, you will get all the details. Later, when I assign a question, I may assign you to do a partition following these rules. You can do it easily. Okay. All right. So let's work on this example. F.4, example for partition. So let's look at the example, concrete example for partition. Look at these elements. 7 elements. All right. Simple example. And based on our arrangement, we use the last element 4 as the pivot. Here, if some of you look at the values, the 4 are pretty much in the middle, right? That's a good thing, right? Some of you may argue, how about you happen to have 1 at the end, or you happen to have 8 at the end, right? then there won't be a good way to do the partition, right? Yeah, we will see that. So those two cases later, when we consider the worst case, we will see, the maximum element or the minimum element at the pivot position. Okay, yeah, we will be there. Here, just the general case. All right. U region, we use different colors to represent 3 different regions. The U region, we just use white color. Okay. Then we need extra space. Just one extra location we use to do swap operation. That's minimum, right? Yeah. When we move elements around, we need to do swap operation. So one extra space. That's pretty good. Yeah, only one, not a big deal. Yeah. All right. Next, let me use the space below to run step by step the partitioning process. All right. When we start, our S region is an empty set. L region is also an empty set. Now let's look at the elements from left to right in the natural order, one by one. Okay, 2 first, then 8, and so on. Okay, one by one. All right. Step 1, let's compare 2 and the pivot element 4. We know it is smaller than 4, so we should move it to S region. So we grow S region by adding this element. Step 2, we compare 8 and the pivot element, it's greater than 4, so we move it to L region. You can see we use 2 different colors to represent these 2 regions. Yellow color for S region and green color for L region. All right, yeah. So you can see the U region is shrinking. Yeah. The other 2 regions are growing. Yeah. Step 3, compare 7 and 4. We move it to L region. Yeah. Natural grow. All right. Number 4, compare 1 and 4. It is smaller than pivot 4. So we move it to S region and we color it in yellow. But when you look at the picture now, you can see it's not in a good way we like, right? It's not desirable. The reason is the green region separate the yellow region at 2 different ends. That's not convenient, right? We want to move all the elements in yellow colors in consecutive locations. And similarly for elements in green color, right? Yeah, so we need to do that step before we process the next element. We need to fix that separation problem. What is the easy way to fix separation problem? Okay. From the picture, can we use some little work to fix it? Okay, yeah. Still, let us use the swap operation. Can you use the swap operation to fix this separation problem? Yeah. The answer is pretty easy. We switch 2 elements. Okay, let us just swap these 2 elements, element 8 and element 1. One swap operation. Okay, we can use that extra space to do the swap operation. Then, after that, we will have the desired state. Yeah, so That's the nice arrangement we like to have. Then we can process the next element in the U region. Step number 5, compare 3 and 4. It should be in S region, and another swap operation, we fix that separation problem. The last element, number 5, in L region, then you can see the U region is gone, right? We have two processed regions, S region, L region, and the elements in each region are in consecutive locations. Yeah, all right. So it's pretty much the end of this partition, but one last step, because we haven't placed the pivot element in place. That step, if we make the pivot element in place, then we're done. Then we will get a perfect partition. All right. To make the pivot element in place, just another swap operation, we can make it. Yeah. Look at that. Look at the picture. It's pretty obvious what swap operation we need to do. These two elements, we apply that swap operation. After that, we have this current state. And this state, that is the desired state we like to have after the partition step. But that is just the one typical partition step, right? We just apply the same process again and again. Think about that recursively, all right? Then the recursion step, that gives us the conquer step in the divide and conquer. So you will see at the end, we sort the whole array. Think about that. At the end, when we apply this partitioning process in various subarrays, then we will get the whole array sorted. Think about that. All right, yeah. So you can see after, this concrete example, we get a whole idea of this quicksort algorithm. Okay, yes. All right. Next, yeah, we need to fix some little technical details, such as this question: how to control S region and L region, right? Yeah, visually, you understand how to manipulate the elements. But in your program, you need to write your code to do it. Here, these two these control these two regions. That's the small little details. We need to have some idea how to update. All right, we use two indices variables to control these two regions. Yeah. So we need to use two or extra space locations, I location and the J location. All right. For S region, we use the original array locations with indices from 0 through I for the S region. L region, we use the locations in the original array from index I+1 through J. Yeah. When we grow S region, we just increment I value. All right. When we grow L region, we increment J value and so on. All right. Yeah. All right. Before final in-place step, yeah, the final in-place step, we need to do something a little different. Yeah. All right. Here, to change I and J values, we grow S region, grow L region, and in the middle, we need to swap two elements. Remember, this step is for that separation problem. Okay, yeah, swap two elements. All right, all right, yeah. And I do not write, how to increment, but that step is trivial, right? It's pretty obvious. So I do not need to tell you, how to change these two values. Yeah, pretty obvious. Yeah. All right. So with that one, so you can see we can easily write the code to implement this quick sort. Although for many high-level languages, the quick sort is a built-in function. Okay? It's a built-in function. Yeah. So you don't need to write a code, but you can just call the existing function directly. Yeah. But we like to learn how to do it. Yeah. Especially, we like to learn the idea, the thinking, yeah, why we do it in this way. All right. And before I move to the next topic, yeah, let me look at another question related to the space, the extra space we used here. Here we use 3 extra space locations. 1, 2, 3. Yeah. That's a constant. That is a constant. So for this problem, we just use 3 extra locations. Yeah. We can describe it as big O of 1, right? Bounded by some constant. Okay, yeah. So that's very little, so we don't worry about this amount of extra space used. Yeah. Then, yeah, I do not remember if I talk about a concept called the in-place algorithm. Probably I skipped that. Yeah. So here I like to talk about this concept, in-place algorithm. Yeah. This in-place, we use this term before for different meaning. An element is in place. Yeah, we use that meaning, but here we use in place for another different meaning. When we describe some algorithm, this in place here means the extra space. Extra. What's the extra space? The space used other than the original input data, because in order to process the given input data, you need to assign certain amount of space anyway, right? Yeah. No matter what algorithm you use. So we do not count that amount of space. Other than that part, if you need to use furthermore amount of space, that's the extra space. So the extra space used by the algorithm is bounded. Yeah, we know bounded is in, that's, yeah, big O of 1. That's the definition of the in-place algorithms. The main property for algorithms in this category. Based on this definition, you can see the quicksort is an in-place algorithm. All right, yeah. So the conclusion, quicksort is in place. Algorithm. All right. Then let's look at the merge sort. Merge sort. Is not. Merge sort is not. The reason, if you recall, the merge sort, when we merge two arrays, look at that. When we merge two arrays, we need to copy data to auxiliary array, to another auxiliary array. The question is, can we eliminate auxiliary array? We cannot. It is extremely hard. So we don't know how to eliminate auxiliary array in the merge sort. So you can see the merge sort does not have this in-place property. In-place property. That's an important property. Okay, so that we can treat as a drawback, a big drawback of the merge sort. All right. Next topic, worst case efficiency of the quicksort. Yeah. So this time we look at the extremal cases. Yeah. That means the pivot element could be the minimum or maximum, the extremal cases. Yeah. All right. So study the worst case. Yeah. Basically, when we do partitioning, the two subarrays after the partition step are not balanced, are unbalanced, are the most unbalanced. That situation would correspond to the worst case. Yeah. All right. Extremely unbalanced case for each partition step. Yeah. For example, here you can see, other than the pivot element, all the elements are in the S region, right? Yellow, in yellow color. No green color element. Okay, so that's one of the extremal cases. Yeah. All right, so we can call S case. Yeah. Yeah. Similarly, we have that L region case as the L case. Yeah. So these two extremal cases, if we have things like this too often, then the overall performance will be very slow. Very, very slow. And finally, we will get a worst case for the quicksort. Yeah. All right. And you can see, we use n-1 comparisons. Yeah. The problem is actually like this. After these comparisons, the size reduction is minimal. Now, the size reduction from original n to n-1, original problem size n data items. But after one partition step, we need to work on another partition on n-1 array. So the size reduction is too slow. So that's tells us why this way will result in the worst case. Yeah. All right. Yeah. So another question. Yeah. But this question, actually, both these two corresponds to the worst case. Yeah. But if we like to compare which one is worse than the other, right? Yeah. They have small difference. The difference is very small. Yeah. Which one is worse or equally bad? Okay. So that's the question. You can look at here to answer this question, you can look at the swap operation. Swap operation, all right? In the first case, that P already in place, right? Yeah. Because the P already in place. But in the second case, P is not in place, right? In order to put the P in place, you need to do one more swap operation. That's the difference. So the difference between these two cases is just a one swap operation. Okay, so you can see the lower one is a little worse than the upper one. Okay, by one swap operation. Yeah. All right. Recurrence equation for worst case. Now we want to see the growth function for the worst case. Growth function. Okay. All right. Running time complexity function. Yeah. Let's say T of n. To sort the whole array, we need to use this many comparisons. Yeah. Then you can see after one partition step, we need to do n-1 comparisons. Okay, so after we spend this much cost, n-1 comparisons, we just reduce the problem size by 1, and we need to apply the recursion on this, slightly reduce the problem another time. Okay, yeah. So that's the recurrence relation. And this recurrence relation is very easy to solve. Yeah, we just do, keep applying this formula again and again, and we will get the final expression of T of n. That's big theta of n squared. It's an n squared efficiency. If you compare with our previous algorithms, you can see it is close to that of the selection sort, bubble sort, and the worst case of the insertion sort. No better than those sorting algorithms for its worst case. Yeah. But its main reason that we use the quicksort, people, still like to use quicksort, is at its extremely good overall efficiency. Overall is good. Yeah. Not because of this kind of efficiency. The overall we can say average. When we say overall efficiency, we mean average case efficiency. Yeah. That is the big theta of n log n. Yeah. N log n. Yeah. So if we look at the big theta of n log n, similar to that of the merge sort, right? Merge sort, we also get big theta of n log n. Yeah. So if we compare their growth functions, we cannot say which one is faster than the other. Yeah. But only when we do experiments, when people write programs to implement the merge sort, quick sort, and the many other sorting algorithms, and run large number of experiments on the same data sets. Yeah. At the end, we will see the quicksort performs the best. Yeah. In that way, we can say quicksort is the fastest. Yeah. From experiments, not from this, asymptotic notation. From asymptotic notation, we cannot tell which one is faster. Yeah. All right. So by the way, here, when I do grading in the homework assignment number 1, I noticed one thing. So here, let me point it out. Yeah. Remember, many questions I gave you ask you to, sort, find a number of comparisons for small number of elements, right? So n equals 4, 5, 6, and so on. But I noticed many students, they apply the formula n log n and plug in those numbers. That's not right, okay? These n log n, they come from the asymptotic notation, right? But when you work on the problems with smaller problem size, concrete, specific problem sizes, you should work on the problems directly, not plug in existing, because asymptotic notation, we use it to tell us the trend when n is very large. You should never apply asymptotic formula for small problem sizes. So that's a common mistake. All right, so never make that mistake anymore. All right, I hope in the midterm you won't do the same way, just plugging numbers in the asymptotic notation, asymptotic formulas. Yeah. All right. Yeah. So we next example for the worst case. All right, before we end this topic, so let me just show you some typical worst case example. Yeah, here let us use this array. You can see 1, the minimum is the pivot. All right, after one partition step, we put a 1 in place. But then the largest element, 8, is the pivot. So another extreme case. So after another partition step, then 2 is the pivot, another extreme case, and so on. You can see for every partition step, we get an extreme case. At the end, we get the worst case. Yeah. So you can see, yeah, worst case is like this one. Yeah. All right. And yeah, so you can see for this kind of data, yeah, this is a descending data, right? Yeah. Similarly, you can consider ascending data. You will get a similar result. Yeah, a little better than this one. If you have ascending data, if we run a partition step, yeah, it will be slightly better than this case. Why? Because there is no swap operation, right? Think about if you have the ascending data, you won't have any swap operation. Here you have a lot of swap operation. Right? That's the main difference. Okay. All right. Yeah. Yeah. So here so that's the final result. Yeah. All the elements are in place. But, first, the size reduction is very slow. Every time we just reduce the size by 1. All right. And the second, we need to do one swap operation in each partition step. Yeah. All right. the last subtopic, best case efficiency of the quicksort. Yeah, so we just look at a little bit, best case. Study the best case. When we get the best case, let us think about that. Yeah. Here, we do not consider the average case because it is too complicated. And for the quicksort, actually, there is no good analysis corresponding to the average case efficiency. There is no good analysis for that part because it's too complex. Yeah. Too hard to do good analysis. Yeah. Yeah. But for the best case, much easier. Best case, we know, we still will look at each partition step. The best thing we like to have is the most balanced partitioning. Yeah. When we split the original array into two subarrays, we like to have the two subarrays have almost equal size, almost equal sizes. Yeah. All right. That's the most balanced partitioning. Yeah. Things like this. Okay. Yeah. It's hard. Yeah. Definitely, it's hard to get the best case. Yeah. Yeah. All right. But we know if the partition step results in a near balanced situation, near balanced, and not necessarily most balanced, then we should have pretty good efficiency. Yeah. All right. Let us do analysis a little bit. Yeah. If we write the recurrence relation, it should be like this one. Yeah. We have some initial values for the t function, and the main recurrence equation is like this. T of n, in order to solve the whole problem with the size m, we need to solve two subproblems with approximately half of the original size, 2 times t of n over 2, and then the cost for the partition step, that's the big theta of m. Yeah. So we go through all the elements. So the big theta of m. Yeah. Then we just need to solve this recurrence relation. Yeah. With some constant c. Okay. Yeah. Here, I like to introduce a special way to get an answer quickly. That's we call it recursion tree method. We interpret this recurrence relation using a recursion tree. All right, so you can see we can assume the n is between two of the adjacent powers of 2 numbers, between 2 to the k and the 2 to the k plus 1. Yeah. For any given n, we can find those 2 power of 2 numbers. Right? Yeah. Because if we start with this inequality, we can get this. How many splits do we need to do? How many splits? How many partitions steps we need to do? Yeah. It can tell us that. Yeah. All right. Now let us draw the recursion tree. Yeah. And at each node, we only put the non-recursion term. Big theta of n, we use constant c multiple of n. All right. Then, when we do one recursion step, we need to solve 2 smaller recursive function calls, right? Yeah, 2 recurrence function calls. Yeah, and their corresponding non-recursion cost. Yeah, so we put in their corresponding nodes. Yeah, and when we split, we can build our recursion tree. Yeah, but when we reach the bottom, we know after this many k times split, we will reach the bottom. This k we can estimate between log base 2 of n minus 1 and log base 2 of n. So we can estimate that k is very close to log base 2 of n. All right. Then let us accumulate all the non-recursion cost. That will be our final cost. Yeah. Each level, we need to add some non-recursion cost. Yeah. Then we add non-recursion cost for all levels. That's our final cost. Yeah. All right. Because each level, the recursion cost is C sub n. So this level, 1/2 plus 1/2, also C sub n. This level, 4 terms Cn over 4, also C. So each level C multiple of n, and so on for all levels. But we have log base 2 of n levels. All right. So that's the estimate of the total cost is big theta of n log n. But that is for the best case. Best case, yeah. The average case also close to this best case, close to, yeah. But really hard to do analysis on it. Yeah. Because we cannot control how the partitioning is, its actual states for different inputs. For different inputs, the actual states, very hard to control for average case. Then it's very hard for us to do good analysis work. Yeah. All right. So after this, we complete this topic, quicksort topic, and the end of module 4. Okay, yeah. This part won't be in our midterm, yeah. But after the midterm, we need to prepare for our next part, yeah. And our final won't be cumulative, yeah. I won't make, comprehensive, accumulative, yeah. So we will test our new materials in module 4. Yeah. So module 4, yeah, starting from module 4, all right? Yeah. Yeah, basically module 4 and module 5. All right. Yeah, module 4 and module 5. Yeah. Yeah. Yeah, because when we move to module 6, we will not have much time left. Yeah. So I will only do a quiz for module 6. Yeah. And for the final exam, I won't include module 6. Final exam, I only include module 4 and module 5. All right. And after the midterm, I need to do quiz number 4 for module 4. Yeah, we haven't done that quiz number 4. Yeah. So we need to have a quiz number 4 for module 4. And after that, homework assignment number 2. All right. Yeah. All right. I have about 15 minutes. So let me do some introduction to new topic. Yeah. the introduction part. Yeah. Next time we will do the implementation details. Yeah. So let me move to module 5. Yeah, just 15 minutes so we can understand our goal. Yeah. What we are going to do. Yeah. All right. All right. Module 5, the topic of the advanced data structure, or S, yeah, more than one. Yeah. Now we will do 2 advanced data structures in this part. Yeah. All right. One is the heap sort. Heap sort, we use the heap data structure. Yeah. Another, the second half. The first 2 parts, part A, part B, we will study heap sort. The second half, another data structure, hashing technology, but the data structure is hash table. All right, the second half of this module. Now, all right, part A, heap sort, part 1. 8.1, introduction to heap sort. Yeah. Let me use this 15 minutes to do this 8.1 introduction. Yeah. We solve our old problem number 4, sort and array. Yeah. But this time, when we consider a different algorithm, we need to provide the reasons why we need to develop a new sorting algorithm, right? You need to have some good reasons. Yeah. Here, let's look at those good reasons. Yeah. Special requirements. Sometimes when you work on your data, you may have some very special requirements. Not usual for your business. You may have special requirements, right? Yeah. If you consider some special requirements, probably you need to consider different sorting algorithm. Here, let me give you the special requirements first. The first requirement, the worst case efficiency must be in big theta of n log n. That's the first requirement. Why this requirement? Because this requirement makes sense because this one we can avoid some bad bottleneck. Right? Yeah. Because if we do not put this worst case efficiency requirement, if you apply some other algorithms, for example, insertion sort and a quick sort, you will get big theta of n squared. That will be very slow. So we treat that kind of efficiency as the bottleneck. We want to avoid that kind of bottleneck. All right? Yeah, if your business, here we just imagine some business requires that. Okay? Some business does not rely on this kind of bottleneck. Okay? So that's the first requirement. Yeah. So look at that merge sort. Merge sort does not satisfy this requirement, right? The merge sort, we know, oh, sorry, merge sort satisfies this. Yeah, merge sort is a good choice for this requirement. Merge sort, we have the worst case, big theta of n log n, okay? But quick sort does not have satisfy this requirement, right? Quick sort does not, okay? Merge sort, yes, okay, all right, yeah. Second requirement, in place. In place. I just give you the meaning of in-place algorithm. The extra space here, let me just put here again, extra space used big O or big theta, big O of 1. That's the second requirement. But for this requirement, we know quicksort satisfies this requirement, but merge sort does not. See, you can see the first two requirements, we filter out both merge sort and quicksort. These first two requirements, we cannot consider either merge sort or quicksort. You can see, yeah, all right, yeah. The third one, maintain dynamic data efficiently. Another special requirement. Dynamic data, what's the dynamic data? The data items keep coming in. So when we work, during the whole working process, we have new data items coming in all the time. Dynamic actually come and go. Think about that. Come and go. That's quite normal, right? In real world applications, that dynamic data behavior, quite normal. Insertion, deletion, frequent insertions and deletions, quite normal, right? Yeah. Here, we want to have efficient manipulations for dynamic data. All right, yeah. So we need to really look at the data operations on dynamic data here. Okay, and what's the meaning? Efficiently, right? How much do you expect? How much work do you expect? You can treat it as efficient. We need to understand that question. Okay, yeah, all right. Because first, for the insertion, when a new data piece comes in, we need to insert that item into our current array. So we need to do insertion. When you do insertion, how much work do you need to do? Yeah, think about that. Yeah. For insertion sort, we need this big theta of n. Insertion sort. That's the average cost. Okay, yeah. But we feel that cost is not good enough. Yeah, insertion sort, that step, big theta of n, not very good when n number is large. We like to have much better one, big theta of log n. Log n, greatly reduced. Reduced from n to log n. We know log n is much smaller than n. That looks good enough. Okay, so here, to answer the question, what do you mean you want to make the data insertion efficient, operation efficient? We want to get this category operations, okay, log category operations. Yeah. All right, the idea. Let's look at the basic idea to solve this problem. Here you can see with these three requirements, special requirements, all our existing sorting algorithms do not satisfy these three requirements. Okay, yeah. So we need to find a new one. Yeah. A new data structure. This time, to solve this problem, we need to consider a new data structure. Now, That means this algorithm relatively more advanced. If we do not use the new data structure, we cannot solve it. We have to start with data structure design. When we design a data structure, we should make it friendly to these three requirements. Supporting, friendly for the solutions, satisfying these three requirements. So here, we want to emphasize the importance of the data structure. All right. The data structure should be a binary tree structure. Why binary tree? Because for the binary tree, we can connect to big theta of log n naturally. Think about when we traverse binary tree from top to bottom. So here I use this term, traverse a binary tree from the root, top is the root, to a leaf. We have a chance to get big theta of m. We just have a chance. Why I say we just have a chance? Because there is one question we need to consider. Is your binary tree balanced? Right? If your binary tree is not balanced, you cannot get this log of n efficiency. Only when your binary tree is near balanced. We do not consider, most balanced. We just consider near balanced. Then we can get that log of n efficiency. All right, so that's the binary tree structure. All right, design of data structure. Okay, this time. Make it as simple as possible. We have some options in our design of data structure, but when we have options, we want to choose relatively simple data structure. Okay, so let's look at the candidates. What kind of options do we have at this point? Remember, we want to represent binary tree structure. Okay, so one is array. One option array. Okay, we can consider. Second, linked list. Linked list. All right, so linked list, because there are pointers used as links point to other nodes. It looks like related to binary tree, right? But here we favor the array data structure, array, because simpler than linked list. Because when we compare these two options, array is much simpler than linked list. There are no pointers, right? In array, we do not need to consider the pointer. In linked list, we need to consider, many pointers. That's not, not quite simple. All right. We want to have a simple solution. So we favor array data structure to represent a binary tree. structure. Yeah. But the question is, can we use an array directly here? Directly? Yeah. To maintain dynamic data? Right? Yeah. Maintain dynamic data? Yeah. The answer is no. Dynamic data efficiently, right? Yeah. Because if we just work on array directly without any special consideration, then the insertion step, we will get big theta of n, right? That's not good. So we don't want to consider that option. But the question is, can we fix it? Right? Yeah. So the current method does not work, but can we modify it to make it work? Right? Yeah. So that will be the answer we will work next time. Okay? Yeah. So we just stop here. We raise the question. Next time we will answer the question. Okay? Yeah. So that's the introduction part. All right. Yeah. Let me stop right here. Remember